Good morning, students. So, on the last turn, we studied about work as force multiplied by displacement, power as work done in unit time, or power is equal to force into velocity, and energy as capacity to do work. Now, in physics, energy is defined as the property of objects which can be transferred from one object to the other object or from one form to another form. Now we are going to study different forms of energy here. So this is the next part of the chapter, different forms of energy. So we go to the next one. So here, the first kind of energy which we are going to study is mechanical energy. Now, when an object can do some work, the object possesses energy. If the object has the capacity to do work, the object possesses energy. And energy possessed by a body due to its state of rest or state of motion is said as mechanical energy. So, energy possessed by a body due to its state of rest when it is not moving, and energy possessed by a body when it is in state of motion together is termed as mechanical energy. Total mechanical energy is the sum of potential energy and kinetic energy. These are the two kinds of mechanical energy which we are going to study right now. But the total mechanical energy is the sum of the potential energy and kinetic energy. So at any place of rest and motion, the sum total will be same. Okay, so that means the energy is conserved. So we move to the other one. So energy possessed by a body by the virtue of its state of rest or of motion is mechanical energy, and this is of two types. The first one is potential energy. Now, if I say a common statement that this child has the potential to do, she can do well, she has the potential, that means she has the stored energy. She can do the work. The same way, potential energy here means the energy is stored in the object when it is in the state of rest. Okay? And this kind of energy is known as potential energy. So, if we have to define, potential energy is the energy stored in an object when the body is at rest or in state of rest. So energy stored in an object due to its state of rest is known as potential energy. Now I am talking about a ball, okay, a ball. The ball has been thrown up, okay. Now, when I throw the ball up, I have given force to the ball and the ball is doing displacement. That means work has been done. Work has been done in throwing the ball up. Now, the work which has been done on this ball, when it is thrown in air, is getting stored in that ball. It starts moving and it is getting stored in that ball. And to the when the ball goes to its maximum height, after which it can't go and it starts returning back to the ground due to the force of gravity, at that maximum point, the potential energy of the ball is maximum. At that point, at that maximum point, the potential energy stored in that ball is maximum, after which the ball starts doing work on its own and it starts falling towards the ground because gravitational pull is pulling the ball towards itself. So at that maximum point, the potential energy in the ball is the maximum. It is stored in the ball and there the potential energy is maximum. So it starts gaining and it is in kinetic energy. It starts gaining energy. It goes to the top. There the potential energy is maximum. And slowly when it is coming down, the potential energy starts decreasing and it starts gaining kinetic energy because it is in the state of motion. Okay. So I think you have understood about potential energy. Okay. Now, potential energy is of two kinds, which we are going to study in the later part of the chapter. So, we said that potential energy is further divided into two parts. One is gravitational potential energy and one is elastic potential energy. Now, what is gravitational potential energy? Gravitational potential energy is the energy due to its position, where the body is placed. So, due to the position of the body, the energy stored in the body due to the position of the body is known as gravitational potential energy, and energy due to the shape and size of the body is elastic potential energy. As we see in the diagrams here, there is a brick which is kept on the top at some height. There is a ground level and the brick is kept at some height. So, some work has been done and the brick has been kept over here, and this brick possesses energy in stored form, and as it is at some height, so there is energy which will be converted to kinetic energy the moment it is left from there. Okay, so when anything is at a height, so this energy is known as gravitational potential energy due to its position. And now in the second one, you can see there is a bow and the arrow has been kept over there and the bow has been stretched. So at this position, when the bow has been stretched, this bow has been deformed. That means the shape of the bow has been deformed because it is a non-rigid body. So, the energy possessed by the bow, because of its shape and size, is known as elastic potential energy. We will study this in detail in the next part of the chapter. So in this figure, we can see there is an elephant. In one figure, the elephant is standing at a height, and in the other one, the elephant is standing on the ground. So the elephant which is standing on some height possesses more gravitational potential energy as compared to the elephant which is standing on the ground. Now, why is this? We are going to study now. Now, we said that potential energy is the energy in the body due to its state of rest. And we know that gravitation is a force of attraction on a body from the center of the earth, isn't it? The work is done on the body in bringing the body towards the center of the earth. So there is a force of attraction acting. Okay, so gravitational pull is the force of attraction which brings the body towards the center of the earth. And potential energy is the energy stored in the body due to its state of rest. So, potential energy possessed by a body due to force of attraction of earth on it is gravitational potential energy. Please try to understand. Potential energy possessed by a body due to force of attraction of earth on it is gravitational potential energy. So if I talk about this figure, the elephant which is standing on the ground, so gravitational potential energy, there gravity is not acting because the elephant is on the ground only. But in the second figure, when the elephant is standing on some height, there is some work done by gravity also. And so it possesses more energy. And that is why the gravitational potential energy for the elephant which is standing at a height is more. I hope it would have been a little bit more clear. Okay. Now, there is a field of gravity. We know this, that the gravitational pull of Earth acts in a certain field. There is a field in which this gravity acts. If a body goes out of this field, this attraction, this pull will not be acting on that body. Okay? So, there is a field of gravity. So, when a body is at infinity, okay, when the body is at infinity, infinite distance, then their acceleration due to gravity is zero. No gravitational pull is acting on that body. So work done by force of attraction of Earth in bringing the body from infinity to that point is gravitational potential energy. Okay? Energy is the capacity to do work. Now we have to study in terms of this, no? So energy is capacity to do work. So work done by force of attraction of Earth in bringing the body from infinity to that point is gravitational potential energy. Okay? So we assume that the body is at some height and the work done in bringing that body from that point to the ground is gravitational potential energy. Okay? Now, as the distance of the body from the surface of the earth increases, it is going higher and higher, the force of attraction will decrease. As it is going higher and higher and higher, the force of attraction will start decreasing. If the body is more, the force of attraction is more. If I am here on the ground, maximum force of attraction is acting on me. And if I come to some height, the force of attraction starts decreasing. And so gravitational potential energy starts increasing. So at a distance, when the body is at a distance from the surface of earth, or when the distance increases, the force of attraction decreases and gravitational potential energy increases. Okay? You have to learn this. You have to understand this properly. Okay? So we go to the next one. Okay, so now we have elastic potential energy. So this is the energy which is possessed by the body when there is a change in shape or size of the body. Okay, when, as in the figure, you can see there is a spring. When the spring is compressed or when the spring is stretched, that means when it is compressed, it is deformed, and when it is stretched, it is deformed. Then work has been done on the spring, which is being stored as potential energy. And when you will leave it, the potential energy will start doing work and it will change to kinetic energy. Okay, so elastic potential energy, when compressed or stretched, a spring gains elastic potential energy. So when an external force is applied on a body and its configuration or shape changes, when an external force has been applied on a non-rigid, when it is non-rigid, then only there will be change in shape and size. So when an external force is acting on a non-rigid body and it gets deformed, there is a change in its configuration or shape. This kind of change, this kind of energy is known as elastic potential energy. Elasticity is the property by virtue of which a body regains its original configuration on the removal of external force. The moment you remove the force, it will come back to its own form, like a rubber band. You stretch a rubber band and leave. The moment you leave, the force has been removed from there, the rubber band comes back to its form. So till the moment you have stretched the rubber band, you have done work on the rubber band, and that rubber band is possessing potential energy in the form of, it is in the elastic potential energy, and the moment you leave the rubber band, it comes back to its normal form, natural form. Okay. So, elasticity is a property by virtue of which a body comes back to its natural form when the force has been removed from it. The potential energy possessed by a body in the deformed state due to the change in its shape and size is called elastic potential energy. Now the things must be clear. So, potential energy is the energy possessed in a body by the virtue of its state of rest. And this is of two kinds. When the body is at some position, it is at some height, then the energy possessed by the body is gravitational potential energy. And when there is a change in shape and size, When the body is in the deformed shape, the energy possessed by the body at that point, when it is in the deformed state and it is in rest, at that point, the potential energy possessed by the body is known as elastic potential energy. Okay. Now, this is equal to the amount of work done in deforming the body or in changing the configuration of the body. So you have to remember, you have to see that work has been done in both the cases. In elastic potential energy, work has been done in deforming the body, and in gravitational potential energy, work has been done in taking the body to some height. Okay, and at that point it is possessing potential energy. Okay, so we move to the next one. Before that, I want to speak about gravitational potential energy and its formula. I have written in one of the slides also. Gravitational potential energy of a body at a height above the ground is measured by amount of work done in lifting it up to that height. I have just now said that the work done in taking it to some point above the ground, that is gravitational potential energy. So the gravitational potential energy of a body at a height above the ground is measured by the amount of work done in lifting it up to that height against the force of gravity. Now, suppose the body has mass m and has been lifted from the ground to a vertical height h. Okay. Now the least upward force F required to lift the body without acceleration must be equal to force of gravity mg. What will be the force applied? Force applied will be mass into acceleration due to gravity. Force is ma, and when we are taking a body to some height, then it will be mg. So force will be mg on the body acting vertically downward, and the work done w on the body in lifting it to a height will be force into the height to which we have taken. So mgh. So work done will be force of gravity mg into displacement h, which comes to mgh. This work is stored in the body when it is at a height h in the form of gravitational potential energy. You already knew this, but I have just mentioned because you should know it in the terms of equation also. So gravitational potential energy is generally written as capital U. It is denoted by capital U, and capital U is equal to mgh, which is the force applied in and the body has been taken to height h. So work done in taking the body to height h against gravity is gravitational potential energy, and it can be measured as U is equal to mgh. Okay, so we move further. Okay, so now we have another form of energy which I am speaking from a long time, kinetic energy. So potential energy was energy possessed by a body when it is in the state of rest. And kinetic energy is the energy possessed by a body when the body is in the state of motion. So when the body is moving, energy possessed by the body when it is in the state of motion is known as kinetic energy. Simple. So a body in motion is said to possess kinetic energy. So energy possessed by a body by virtue of its state of motion is called kinetic energy. It is usually denoted by the symbol K. For example, you can see here, this boy is bringing this hammer with great force towards the ground. So the boy has done some work and has brought the hammer to the ground. Now, the work done in bringing the hammer from some place to the ground work has been done and work has been stored in this, and when it has been brought over there, it is in motion, and the moment it will strike the ground, it will leave some impression on the ground. So work will be done. Okay. So capacity to do work is energy, and when this hammer is having kinetic energy, it has been brought from a position and it is striking the ground, then it is leaving an impression on the ground. Like a fast moving stone has the capacity of breaking a window pane on striking it, and thus it possesses kinetic energy. And you can see in the other one, this boy is doing skating on an inclined plane. So the boy is also moving, so possessing kinetic energy. Okay. Now we are going to find out the formula for kinetic energy. How to calculate, how to find out what is the kinetic energy. So we are going to the next slide. Okay, so we studied that kinetic energy possessed by a moving body can be measured by the amount of work which the moving body can perform before coming to rest. Okay, so hammer was coming. So before the hammer is coming to the coming to the ground, coming to the rest position, the hammer has left some impression to the ground. So kinetic energy possessed by the moving body can be measured by the amount of work which the moving body can perform before coming to rest. Now to calculate it, an opposing force is applied to stop the body, and the amount of work done by opposing force is calculated. Okay. So to calculate the kinetic energy, we are calculating the opposing force. Okay. An opposing force is applied to stop the body. There is some force which is stopping the body. So an opposing force has been applied to stop the body, and this amount of work, which is the opposing force, is calculated. Now, let us assume, suppose a body of mass m. So we assume there is a body which is having mass m, is moving with velocity v. Mass is m and velocity is v. It is brought to rest. Okay, the body has been brought to rest by applying a constant opposing force F. Okay, so the body has been brought to rest by a constant opposing force F. Okay, so there will be retardation. Okay, now let A be the uniform retardation produced by the force, and the body travels a distance s. So s is the distance, a is acceleration, so retardation will be minus a. Body has mass m and is moving with velocity v, and finally the body has been brought to rest because retardation has been applied. Now, in this position, the kinetic energy of the body, which has to be calculated. So kinetic energy of the body will be work done by the retarding force. Some work has been done over there, no? So the work done by the retarding force is the kinetic energy of the body. Yes? So the kinetic energy is calculated as work done by the retarding force. Now how to calculate it? Work done will be force into displacement, that is F into S. So kinetic energy, we have taken K over here. Force is F and displacement is S. Now when retarding force F is ma. We know that F is equal to ma. So we take retarding force is equal to ma. Now to calculate displacement, we will apply V square is equal to U square plus 2as. You have studied this equation in class 9. Now, according to our assumption, our initial velocity is V and our final velocity is 0 because the body has been brought to rest. So final velocity is 0 and initially the body was moving with V and acceleration is A, so retardation is minus A. Okay, so from the relation we get V square is equal to U square plus 2as. So final velocity here is 0, so final is 0. Initial velocity here is V, so V square minus, because A is minus, so minus 2as. Okay, so 0 is equal to V square minus 2as. Okay. Now from here S can be calculated as V square by 2a. Now substituting the values of F and S in the equation K is equal to F multiplied by S, we get F as ma and S as V square upon 2a, and we can see A and A is cancelled and we get half mv square. So kinetic energy is half mv square. Please remember, kinetic energy formula is half mv square, where m is the mass of the body and v is the velocity of the body. Potential energy U was mgh. Kinetic energy is half mv square. Okay. So we move to the next part of the chapter. So now we have a relationship between kinetic energy and momentum. Momentum we have studied earlier. Have we studied momentum? Momentum is P is equal to m into V. Okay, and kinetic energy we have just now calculated K is equal to half mv square. Now let us see the relation between kinetic energy and momentum. Let a body of mass m be moving with velocity v. In that case, kinetic energy K is half mv square and momentum P is equal to mass into velocity, that is m into v. Now substituting the values of v will be P by M. So substituting the value of V in K is equal to half mv square, we get K is equal to half m in bracket P upon M whole square. In place of V, we are writing P by M. So half m P by M whole square, which comes as half m P square upon M square. M and M will be cancelled. So we will have K is equal to P square upon 2M. So when we take it to the other side, it becomes P square is equal to 2mk. Thus, kinetic energy K and momentum P are related as P is equal to under root 2mk, or K is equal to P square upon 2m. You have to again remember this relationship. It may be asked as it is, and few numericals can also be asked on this formula. Okay, so we move to the next part of the chapter. Now we have work energy theorem. This is also important here. Now suppose a body is moving. A body is moving with velocity v. Okay. Now some force has been applied on the body in the direction of motion. What will happen? The body will start moving with greater acceleration. The acceleration will increase because we have applied force in the direction of motion. Yes? So, when a force is applied in the direction of motion of a body, it accelerates and thus increases the kinetic energy of the body. There will be an increase in the kinetic. Already the body was moving, so there was kinetic energy, and when force has been applied in the direction of the motion, the kinetic energy increases. This increase in kinetic energy is equal to the work done on the body by force. This increase in kinetic energy is the work done on the body by force. So, according to work energy theorem, the work done by force on the moving body is equal to the increase in its kinetic energy. Okay? Now we are going to calculate this. Now again, let us suppose body of mass m be moving with initial velocity u when a force F is applied on the body along its direction of motion. Okay, so a body of mass m and initial velocity u is moving and a force F has been applied on the body in the direction of motion, and it produces an acceleration A, and the velocity of the body changes finally to v. Now from u it has changed to v in moving distance s. So in this case, work done by force will be force into displacement. The same formula to be applied everywhere, force into displacement. That is W is equal to F multiplied by S. Now again we have to calculate S. So V square is equal to U square plus 2AS, the same equation. Now from here we get S is equal to V square minus 2 square upon 2A. V square minus U square upon 2A. Now F is equal to MA. We all know F is equal to MA. Now we will put these two values of F and S in the same equation. W is equal to F multiplied by S. We get MA into V square minus U square upon 2A. So we get half M, A and A is cancelled, half M V square minus U square, and when we multiply by half M inside, we get half MV square minus half MU square. Now half MV square is kinetic energy. Half mu square is also kinetic energy. Kinetic energy is half mass into velocity square. So from here, final kinetic energy minus initial kinetic energy is equal to work done on the body by force. So we have calculated work done on the body is equal to final kinetic energy minus initial kinetic energy. Now simply the numericals will be given in the same way, and you have to calculate the work done by calculating final kinetic energy, initial kinetic energy, and by subtracting you will get the answer. Okay. So in continuation of this only, I will like you people to know there are three forms of kinetic energy. Very easy, we all have done this, so it won't take time. So there are three forms of kinetic energy. Number one is translational kinetic energy. Now you know the word translation. So when the body is moving in a straight line path, at that time kinetic energy possessed by the body will be known as translational kinetic energy. Simple. Translation means straight line. So when a body is moving in a straight line, the energy possessed by the body at that time is translational kinetic energy. Example, car moving on a straight road. Second, rotational kinetic energy. If a body rotates about an axis, this is known as rotational motion. We have already studied, and the kinetic energy possessed at that time is known as rotational kinetic energy. A spinning top, potter's wheel, Okay. And the third is vibrational kinetic energy. When a body moves to and fro from its mean position, at that time kinetic energy possessed by the body is vibrational kinetic energy. Okay. Suppose you have taken a rubber band, you have stretched and you have fixed the rubber band from two stretched pins, and then you are plucking the rubber band from between. That is doing vibrational kinetic energy, isn't it? So translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. Okay. So we move to the next part. So now we have conversion of potential energy into kinetic energy. Now in the beginning only, I mentioned an example when a ball is thrown in air. Okay. Now you will understand the example better now. At that time you were not knowing. So when a ball is thrown up, the ball has been given some force. I have thrown the ball with force. So I have done work on the ball. Now, with that work, the ball possesses kinetic energy, and so the ball is moving up in the air. So, at the time when you have given force to the ball and the ball is doing displacement, work has been done on the ball, which is in the form of kinetic energy. So kinetic energy is maximum when the ball starts moving up in the air. And slowly, the kinetic energy is decreasing and potential energy in the ball is increasing. Now, at a time, the ball will reach to a place and it can't go higher now. And from that point, the ball will start returning to the ground. So that maximum point will be the returning point of the ball. And at that point, the ball will have the maximum potential energy. This is what I was talking in the previous slide. So at that point, the ball will have the maximum potential energy and it will be stored in the form of work done, and the moment it reaches there, it will start returning back and the potential energy will start decreasing, and again the ball will have increased kinetic energy. So while going, kinetic energy was maximum and it was slowing down slowly, it was decreasing and potential energy was increasing. Finally, all the kinetic energy was changed to potential energy, and from that point, potential energy, the stored potential energy started doing work, and slowly, potential energy was decreasing and it was kinetic energy increasing, and finally, it was maximum kinetic energy, and the ball comes to stop the moment it strikes the ground. Okay, so this way potential energy can be changed to kinetic energy and kinetic energy changes to potential energy. The total energy remains the same at all the points. At all the points, potential energy, the sum of the potential and kinetic energy remains the same. So potential energy changes into kinetic energy in few of the examples. Now let us see. In this diagram, you can see this man which is jumping. So the man which is in the standing position is possessing potential energy. He has climbed the stairs and some work has been done, and so he possesses potential energy. The moment he jumps, the potential energy is converted to kinetic energy. There are few more examples. A wound-up watch spring has elastic potential energy because of its wound-up state. You give windings to this watch now, and then it is in the wound-up state. As the spring unwinds itself, the potential energy stored in it changes into kinetic energy. It starts coming back into its original form now. So it does work and the potential energy starts converting to kinetic energy. Another example, when the string of a bow is pulled, some work is done which is stored in the deformed state of the bow in the form of its elastic potential energy. On releasing the string to shoot an arrow, potential energy of the bow changes into kinetic energy of the arrow, which makes it move. One more example. A compressed spring has the elastic potential energy due to its compressed state. When you have compressed the spring, it is having elastic potential energy. You have compressed it, you have deformed it, and it is stored as potential energy. The moment you release it, the potential energy starts changing to kinetic energy, and work has been done. Okay, so this way potential energy changes to kinetic energy. Okay, so I stop here today. This is a big chapter, so we have to do it in parts. I had given you homework yesterday, so I hope that you must be continuing with that work only. So I'm not giving you any homework today. Continue with those numericals. Go through the chapter. Whatever I have done today, if you go through the chapter, you do 1 or 2 readings of the chapter, the things will be very clear to you. If still you have some problem, please do ask. Okay? So thank you so much. Take care. Bye-bye.